Chapter 24, comparing means. We're looking at a two-sample t-test for means, and it's a difference of means. So we're finding two means of independent populations, and we want to know if the difference is significant. So the hypotheses are very similar to the hypotheses of our two-prob z-test. Instead of P and P1 and P2, we're looking at mu1 and mu2. So it's mu1 minus mu2 equals 0, or mu1 equals mu2. And then mu1 minus mu2 is not equal to 0. It can also be less than or greater than. It's important that you identify what mu1 and mu2 are if they are not if it's not clear. So if you're going to use mu1 and mu2, you need to say mu1 is women, mu2 is men. If you use mu w and mu m, then you don't have to define that because it's clear. The conditions are the same as our t-test, but we have to check them for both groups. We need to have independence of each other. The two groups need to be independent of each other. And then each group must be less than 10% of the population. Each group has to be randomized, so a simple random sample for each group or a randomized experiment. And we saw in the last test that it's really important that you not use simple random sample when you're looking at a randomized experiment. You have to differentiate between those two. And then nearly normal, you have to look at a graphical display of each set of data. So you should have two graphs in this one. It's either a histogram, that's usually the better one. Histogram, dot plot, stem and leaf display, you probably don't want to spend the time to make those, or the normal probability plot. The normal probability plot is the last one in your stat plot menu. And then you have to draw both of them. Sketch both of them. Don't just look at the calculator and say, oh, it's met. So our formula for adding two standard deviations comes from our chapter 16 formula here, the square root of sigma 1 squared plus sigma 2 squared. But from last chapter, our equation was S1 over the square root of n, or S over square root of n. So I want to know the standard error of the difference between two means. I have S1 over the square root of n1 squared, because that's sigma squared, and S2 over the square root of n2 squared. And when I square these, I end up with S1 squared over n1 plus S2 squared over n2, all under a big square root. We're not going to pull the variances because for the means, it would require the assumption that the variances are equal, and that's not necessarily true. For the proportions, the standard deviation and standard error is dependent on the proportion. So if the proportions are equal, then the standard deviations would be equal. But that's not necessarily true for means and standard deviations. With the mean, you can have two different means and have your two means that are the same, and the variances could be the same, or they could be different. And you could also have two different means that have the same variation. So we don't pool the data on these ones. The test statistic, that is your t-score. It's the same general idea as our z-score. It's the y1 minus y2 minus your hypothesis, which is 0, over the standard error, which you insert the formula from the last one. And then you can use TCDF to find the p-value. The degrees of freedom are n1 plus n2 minus 2. This is just a rough estimate. The calculator actually gives us the more accurate degrees of freedom, but that really comes from your n1 minus 1 plus your n2 minus 1. And if you put that together, you have n1 plus n2 minus 2. So you have two samples. Now you're going to subtract 2. That gives us a good estimate of what to use. So here's our first example. The resting pulse rate for a random sample of 26 smokers had a mean of 80 beats per minute. So we have a mean of 80 beats per minute and a standard deviation of 5, and that was 26 smokers. And then 32 randomly chosen non-smokers, the mean and standard deviation were 74 and 6. Both sets of data were roughly symmetric and had no outliers. This is an important information because it's telling us that our nearly normal condition is met. Is there evidence of a difference in the mean pulse rate between the smokers and non-smokers? Evidence of a difference, and that tells us that our alternative hypothesis is going to be not equal to. Okay, so we're going to write our hypotheses. Our null hypothesis is that the mean of the smokers minus the mean of the non-smokers is equal to 0. And the alternative hypothesis is that the mean for the smokers minus the mean for the non-smokers is not equal to 0, and it's not equal to because it just asked about a difference. Now, I defined S and NS. Those kind of make sense with the problem, so I don't have to separately write out what that is. But if I were to use mu1 and mu2, I would need to say mu1 is smokers and mu2 is non-smokers. So our important information here is that X bar for smokers is 80, and the standard deviation for smokers is 5, and N for smokers is 26. And then the X bar for the non-smokers is 74. The standard deviation for non-smokers is 6, and the number of non-smokers was 32. And we'll set our alpha at 0.05, and then we'll check our conditions. So the group of smokers, heart rate is independent of the non-smokers' heart rate. Um, 26 is less than 10% of all smokers. And 32 is less than 10% of all non-smokers. Both samples were random. It says random sample, randomly chosen. So both samples are random. And then it states that both sets of data are roughly symmetric with no outliers. So since conditions are met, a T model is appropriate. I will use a two-sample t-test for difference of means with, let's see, our sample size is 26 plus 32 minus 2, which is 52 degrees of freedom. I'm sorry, 56. So 56 degrees of freedom. Okay, and I like to just put that in the statement so I have it somewhere. So then my difference of means, my X bar S minus X bar NS is 80 minus 74, which is 6 beats per minute. That's our sample difference. So we need to find the probability of getting this sample difference if the null hypothesis were true. Move some things out of the way. So our standard error of X bar S minus X bar NS was the square root of S squared, so 5 squared over 26 plus 6 squared over 32. I'm going to do that in the calculator. Okay, so we got 1.44. And so our t-score is the difference, 80 minus 74, over 1.44, which is 6 over 1.44, which is 4.154. And then to find our p-value, we're going to do TCDF, and it's not equal to, so we're going to do our t-score comma 99, because our t-score is positive, so 4.154 comma 99 comma our 56 degrees of freedom, and then we're going to times that by 2 because it was a not equal to. We get, make some space here, 5.639 times 10 to the negative 5, and we're going to times that by 2, and we get 1.128 times 10 to the negative 4, which is 0.00011128. So we'll write our conclusion with that p-value. So my p-value is 0.00011128, which is clearly very small. So we're gonna, what just happened? We're gonna write our conclusion. Since my p-value of 0.00011128 is less than my alpha was 0.05, this is much smaller, of 0.05, I reject the null hypothesis. Oops. There is enough evidence to convince me there is a difference in the mean pulse rate or mean heart rate of smokers and non-smokers. What does our p-value mean? I don't know why that came up. If there is no real difference in the heart rate of smokers and non-smokers, that's our null hypothesis, there is a 0.00011128, our p-value, chance of obtaining our sample difference a sample difference as surprising or more surprising than 6 beats per minute more for smokers. And so that's our conclusion and our p-value. Follows the same general principles that we've been doing in the proportions, except for now we're talking about means. And so we need to make sure we put units on it. And so let's create a confidence interval. Our confidence interval is our difference, our xs bar minus xns, plus or minus our t star with 56 degrees of freedom times our standard error of x bar s minus x bar ns, which was 6. Our difference in the means was 6 beats per minute, plus or minus, I'm going to have to look at a table for that t star, and then my standard error was 1.444. So let's pause and find a t-table. So I'm looking at the t-table in the back of the book. I have 95% confidence, and the book only has 50 and 60, so I'm going to go to 50 degrees of freedom, and I'm going to use 2.009. So that's the t-star with 50 degrees of freedom 95% confidence was 2.009 from my table. And then I can do those calculations. 6 plus 2.009 times 1.444, and 6 minus, so I get 3.0, it's really 3.1 because it's 0.99, so that rounds up, and 8.9. Okay, so what does that mean? That means that I am 95% confident, because I did a 95%. The true mean heart rate for smokers is between, so I did smokers minus non-smokers, so a positive means the smokers is higher, 3.1 and 8.9 beats per minute higher than the true mean heart rate for non-smokers. Okay, and that's our full hypothesis test, including the confidence interval. Now this can all be done in the calculator as well, and we'll talk about that with the next example. This one we'll do by hand. So here's our next example. We're going to do this one in the calculator because it has data. Here's the saturated fat content for several types of pizzas sold by 2 national chains. Determine if there's evidence of a difference. So again, evidence of a difference. So that's our alternative hypothesis in saturated fat content for the 2 brands. Brand D, there's the data, and brand PJ, there's the data. So right now, pause the video and put this information into your calculator. Okay, now that that's in the calculator, you want to make sure you report the means and standard deviations. Even if you're going to do the whole thing in the calculator, you need to state what those things are. So let's first talk about our hypotheses. Our null hypothesis is that mu for D minus mu for PJ is equal to 0. And our alternative is that it's not equal to 0. And we'll set an alpha of 0.05. And then we can look at our conditions. Okay, our conditions, I'll type these because it just looks better. The fat content for brand D is independent of brand PJ. Let's see, what were our sample sizes? 15 on PJ, and the sample size is 20. So 20 is less than 10% of all brand D pizzas, and what did I say, 15 is less than 10% of all brand PJ pizzas. There's technically an unlimited number of combinations, right? I mean, the number of combinations is huge, so if you're randomly choosing 2 of these, or 20 of them, then that's fine. So your sample is representative. Samples are representative. Let's change that. Of both brands. And now we need to look at the data and the normal probability plots. So I'm going to add in a video here. Okay, so we're going to our second stat plot. Turn my plot on. It's already, this one here is my normal probability plot. My first set of data is list 1, and then I'm going to zoom 9, which is zoom stat, and that looks pretty straight. So I'm going to pause that, and then I'm going to draw it. Okay, so this is brand D. It's straight enough. And then let's add another one and look at our, let's look at our other one. Stat plot. Just going to turn this one to list 2, second 2, zoom 9, and that also looks pretty straight. That one's a little blurry, but you get it. So I'm going to draw this. And that's brand PJ, and it's also straight enough. So nearly normal checks. So then we can say, since conditions are met, AT model is appropriate. I will use a two-sample t-test for difference of means, because we're taking two means and comparing them, subtracting them with, let's see, we have 20 and 15, so that's 35 minus 2, which is 33 degrees of freedom. Okay, and so then we can now do our test, and I'm going to go to a new page for that, because I'm going to show you how to do this in the calculator. Okay, so in our calculator again, now we're going to go to stat, tests, two-sample t-test. We're not really going to use the two-sample z-test. We're not going to use the z-test. It's t-test for the one sample, and it'll be t-test for matched pairs in chapter 25. And then it's two-sample t-test for the difference of means. And so I have the data. I have the data in list 1 and list 2. I could enter the stats if I wanted. And then my null hypothesis is not equal to. It's really important that we change that. This is the number one mistake in the calculator, is not changing the alternative hypothesis here. And then I'm going to calculate. So I'm going to write that down. This is our important information. Now you can't take a picture of it, so you have to write it all down. We're going to say that our two-sample t-test, and we're going to write t equals 4.823 and p equals 3.15 times 10 to the negative 5. Don't leave that part off. It's really important. And then we want to write our degrees of freedom are actually 32.757, which is really close to the 33 estimate. And then our x bar, we didn't write this down anywhere, so you want to write down your stats. X bar D is 11.25, SD was 3.193, and X bar PJ is 6.533, and SPJ is 2.588. And then if I scroll down, it just gives me N. So if you have it in your calculator, it just tells us that ND is 20 and NPJ is 15. And so we have a small p-value, therefore we're going to reject the null hypothesis. We don't believe there's a difference. Or we do believe there's a difference. And then what do we believe that difference is? And we'll show you how to do that confidence interval in the calculator as well. So as we type up our conclusion here, so since my p-value of 0.0000315 is less than my alpha of 0.05, I reject the null hypothesis. There is enough evidence to convince me there is a difference in mean saturated fat content of brand D and brand PJ pizza. And if that's just my p-value interpretation, there was no difference in, can I copy some of this? Getting lazy. Mean saturated fat content of brand PJ and brand D pizza. There is a 0.000315 chance of obtaining a sample difference as surprising or more surprising than, and our sample difference is 11.25 minus 6.5. So 11.25 minus 6.5, about 4.75. 4.75 grams more in brand D pizza. It was positive, so brand D had more. And I'll just do this and move it down, hopefully. There we go, so we can read it. So that means I can make a confidence interval as well. And here's the nice thing about the calculator. So back to looking at the calculator, I'm going to go to Stat, Tests. I'm going to go down to the 2-sample t interval, and then hit Enter. And I have the data. I want 95%. I mean, what if we did 99%? We're looking at a really, really small p-value. So let's do 99% just for the fun of it. And calculate. And then we will write down that information. Sorry, it's blurry. So we get 2 sample t interval, degrees of, oops, I forgot to write it down, 2.0427, comma, 7.3906. Degrees of freedom, again, are 32.757. And then we're going to interpret that interval. I am 99% confident the true mean saturated fat content in brand D is between 2.04 and 7.39 grams higher than the mean saturated fat content in brand PJ. So again, we subtracted D minus PJ. So D, it's positive, so D is higher. And you could state it the other way around. You could say, I'm 99% confident the true mean saturated fat content in brand PJ is between 2.04 and 7.39 lower than the mean saturated fat content in brand D. So you can state them either way, depending on how you subtract, and it still means the same thing.